According to the 2002 National Electrical Code, NEC, specifically Section 314.28, in non-metallic enclosures, a bonding jumper, sized in accordance with Table 250.122, shall be used to connect the equipment grounding conductor to the box. This indicates that a grounding screw with pigtail is required in non-metallic junction boxes. It is important to understand the code requirements to ensure electrical safety and compliance. Some may mistakenly believe that if you run metal conduit, the conduit is considered grounded, and thus a ground screw in every junction box is not required, and that the same answer applies if you're running MC cable. However, the journeymen who state that grounding screws are not required with metal conduit or MC cable are incorrect. Section 250.110 of the 2002 NEC states that electrical continuity of metal raceways and cables, metal raceways, cable armor, and other metal enclosures for conductors shall be electrically continuous throughout their length and shall be connected to all boxes, fittings, and cabinets so as to provide a continuous electrical path to ground. This requires that all metal raceways and enclosures be properly grounded, regardless of whether they are used as the grounding conductor. Therefore, based on the NEC 2002, grounding screws with pigtails are required in both metallic and non-metallic junction boxes. The use of metal conduit or MC cable does not exempt the need for proper grounding. It is always recommended to refer to the latest version of the NEC for the most current requirements. Now, let's delve deeper into the grounding requirements for metal junction boxes according to the NEC 2002 and related sections. Grounding, in essence, is the process of creating a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Without proper grounding, fault currents can linger, creating a shock hazard and potentially damaging equipment. When dealing with metal junction boxes, several NEC sections come into play. Firstly, consider Section 250.4, which outlines the general requirements for grounding and bonding. It emphasizes the need to create a low impedance path and to ensure that the electrical system is free from objectionable current. Now, diving into Section 250.118, we find a list of acceptable grounding conductors. This section specifies which types of conductors can be used for grounding purposes, including metal conduits, metal raceways, and equipment grounding conductors. It's important to use conductors that meet the requirements outlined in this section to ensure effective grounding. Next, let's explore Section 250.146, which addresses the grounding of equipment connected by cord and plug. While this section primarily focuses on cord and plug connections, it provides valuable insights into how equipment grounding should be handled. This section emphasizes the need for a reliable grounding path, regardless of whether the equipment is hardwired or connected via cord and plug. Furthermore, Section 314.40 covers the installation of boxes and conduit bodies. This section provides specific guidelines for securing and supporting boxes, as well as for connecting conduit to boxes. It's essential to follow these guidelines to ensure that the grounding system remains intact and effective. Now let's talk about grounding electrodes. Section 250.50 outlines the requirements for grounding electrode systems. This section specifies which types of electrodes can be used for grounding, such as metal underground water pipes, ground rings, and rod and pipe electrodes. It's crucial to select an appropriate grounding electrode system based on the specific conditions at the installation site. Moving on, Section 250.64 addresses the grounding electrode conductor. This section provides guidelines for sizing and installing the conductor that connects the grounding electrode to the electrical system. It's important to use a conductor that is large enough to handle the expected fault current and to protect it from physical damage. Additionally, Section 250.92 covers bonding of equipment grounding conductors and enclosures. This section emphasizes the need to bond all metal parts of the electrical system together to create a common ground. This helps to minimize voltage differences and to prevent shock hazards. In the context of metal junction boxes, this means ensuring that the box itself is properly bonded to the equipment grounding conductor. Now let's address the specific question of whether a grounding screw with pigtail is required in metal junction boxes. As we've established, section 250.110 mandates that all metal raceways and enclosures be properly grounded. This means that the metal junction box must be connected to the equipment grounding conductor in a way that ensures electrical continuity. While metal conduit can serve as a grounding conductor, it's not always sufficient to rely solely on the conduit connection. A grounding screw with pigtail provides a more positive and reliable connection to the equipment grounding conductor. This is especially important in situations where the conduit connection may become loose or corroded over time. Moreover, a grounding screw with pigtail allows for easy connection of multiple equipment grounding conductors within the junction box. This is often necessary when there are multiple circuits or pieces of equipment being served from the same box. Without a grounding screw, it can be difficult to make secure and reliable connections to all of the equipment grounding conductors. In summary, while metal conduit can contribute to the grounding system, it's not a substitute for a proper equipment grounding conductor connection within the metal junction box. A grounding screw with pigtail provides a more positive and reliable connection, and it allows for easy connection of multiple equipment grounding conductors. Now, let's further examine the nuances of grounding metal junction boxes according to the NEC, while recognizing the importance of consulting the latest version of the code for the most up-to-date information. When we talk about grounding, we're essentially referring to the intentional connection of electrical systems and equipment to the earth. This connection provides a safe path for fault currents to flow, minimizing the risk of electrical shock and equipment damage. Grounding ensures that metallic enclosures, like metal junction boxes, are at the same electrical potential as the earth, preventing dangerous voltage differences. Section 250.4a of the NEC emphasizes the importance of grounding electrical systems to limit voltage imposed via lightning, line surges, or unintentional contact with higher voltage lines. This grounding helps stabilize voltage to earth during normal operation. Subsections 2, 3, 4, and 5 of this section provide further requirements in achieving a grounded system. Now let's dive into the specific components of a grounding system within a metal junction box. The grounding electrode system, as detailed in NEC Article 250, Part Roman 3, serves as the foundation for grounding. This system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are buried in the earth. These electrodes provide a low impedance connection to the earth, allowing fault currents to dissipate safely. The grounding electrode conductor, as specified in NEC Article 250, Part Roman 4, connects the grounding electrode system to the electrical system. This conductor must be of sufficient size to safely carry the maximum fault current that could occur. It is typically made of copper or aluminum and must be protected from physical damage. Within the metal junction box, the equipment grounding conductor EG plays a crucial role. The EGC is a conductive path that connects the non-current carrying metal parts of equipment to the grounding system. This includes the metal enclosure of the junction box, as well as any metal equipment or appliances connected to the electrical system. The EGC provides a low impedance path for fault currents to flow back to the source, tripping the overcurrent protective device such as a circuit breaker or fuse. NEC Section 250.118 lists the types of acceptable equipment grounding conductors, including wire, rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit, under certain conditions. The grounding screw with pigtail, often referred to as a grounding screw with a bonding jumper, serves to connect the EGC to the metal junction box. The screw provides a secure mechanical and electrical connection, ensuring that the metal box is properly grounded. The pigtail, or bonding jumper, is a short length of wire that extends from the grounding screw to the EGC. This pigtail allows for easy connection of the EGC to the grounding screw, even in tight spaces. The size of the grounding screw and pigtail must be appropriate for the size of the EGC, as specified in NEC Table 250.122. This table provides minimum sizes for equipment grounding conductors based on the rating of the overcurrent protective device protecting the circuit. Now let's address the specific requirements for grounding metal junction boxes when metal conduit is used. While metal conduit can serve as an equipment grounding conductor under certain conditions, it is not always sufficient to rely solely on the conduit connection. NEC section 250.134 requires that metal enclosures, including metal junction boxes, be grounded by one of the methods specified in section 250.130. These methods include connecting the enclosure to the EGC using a grounding screw with pigtail, or by bonding the enclosure to the metal conduit using a listed fitting. Even when metal conduit is used as the EGC, it is still recommended to use a grounding screw with pigtail in a metal junction box. This provides a redundant grounding path, ensuring that the metal box is properly grounded even if the conduit connection becomes loose or corroded over time. Furthermore, a grounding screw with pigtail allows for easy connection of multiple EGC within the junction box. This is often necessary when there are multiple circuits or pieces of equipment being served from the same box. Without a grounding screw, it can be difficult to make secure and reliable connections to all of the EGC. In summary, while metal conduit can contribute to the grounding system, it is not a substitute for a proper EGC connection within the metal junction box. A grounding screw with pigtail provides a more positive and reliable connection, and it allows for easy connection of multiple EGC. Therefore, it is generally recommended to use a grounding screw with pigtail in all metal junction boxes, regardless of whether metal conduit is used as the EGC. Now let's delve into the specific code sections within the NEC that elaborate on these requirements. NEC section 314.40d addresses the connection of metal boxes. This section requires that metal boxes be effectively grounded and bonded to the equipment grounding conductor. It specifies that connections to metal boxes shall be made with fittings that are identified for grounding. NEC section 250.8 provides general requirements for bonding. This section requires that bonding be provided when necessary to ensure electrical continuity and the capacity to conduct safely any fault current likely to be imposed. NEC section 250.96 specifically addresses bonding of metal enclosures. This section requires that metal enclosures containing service conductors be bonded to the grounding electrode conductor. It also requires that metal enclosures containing other than service conductors be bonded to the equipment grounding conductor. NEC section 250.148 addresses continuity and attachment of equipment grounding conductors to boxes. This section requires that equipment grounding conductors be connected to all boxes that are part of the circuit. It specifies that connections shall be made so that the electrical continuity of the grounding path is not interrupted. Furthermore, this section clarifies that where more than one equipment grounding conductor enters a box, all such conductors shall be spliced or joined within the box or to the box with devices suitable for the purpose. The NEC provides clear and comprehensive guidelines for grounding metal junction boxes. By following these guidelines, you can ensure that your electrical system is safe and compliant. Remember to always consult the latest version of the NEC and to seek guidance from a qualified electrical professional when working with electrical systems. The principles remain consistent across different editions, but specific requirements may evolve. Now, let's examine the practical implications of these code requirements in a real-world scenario. Imagine you are installing a new lighting circuit in a commercial building. The circuit will be fed from a panel board located in the electrical room, and it will serve several recessed LED light fixtures in an office space. The wiring method will be rigid metal conduit, RMC, which will be run concealed above the ceiling. As you install the RMC, you will need to install several metal junction boxes to make splices and terminations. These junction boxes will be used to connect the RMC to the light fixtures, as well as to make any necessary wire splices. According to the NEC, each of these metal junction boxes must be properly grounded. This means that you will need to connect an equipment grounding conductor to each box, ensuring that the box is electrically connected to the grounding system. To accomplish this, you would typically use a grounding screw with pigtail. The grounding screw would be installed in a pre-tapped hole in the metal junction box, and the pigtail would be connected to the equipment grounding conductor. The equipment grounding conductor would then be connected back to the panel board, where it would be connected to the grounding bus. In this scenario, the RNC also serves as an equipment grounding conductor. However, it is still necessary to install a grounding screw with pigtail in each metal junction box. This provides a redundant grounding path, ensuring that the box is properly grounded even if the RNC connection becomes loose or corroded. Furthermore, the grounding screw with pigtail allows you to easily connect the equipment grounding conductors from the light fixtures to the grounding system. This ensures that the light fixtures are also properly grounded, minimizing the risk of electrical shock. As you install the metal junction boxes, you would need to carefully inspect each connection to ensure that it is tight and secure. You would also need to verify that the equipment grounding conductor is properly sized and installed in accordance with the NEC. Once the installation is complete, you would need to test the grounding system to ensure that it is functioning properly. This can be done using a ground impedance tester, which measures the resistance of the grounding path. If the resistance is too high, it indicates a problem with the grounding system, which must be corrected before the circuit is energized. By following these steps, you can ensure that the lighting circuit is safe, compliant, and reliable. Grounding is a critical aspect of electrical safety, and it is essential to take the time to do it right. Now, let's address some common misconceptions about grounding metal junction boxes. One common misconception is that if you are using metal conduit, you do not need to ground the metal junction boxes. As we have discussed, this is not correct. While metal conduit can serve as an equipment grounding conductor under certain conditions, it is not a substitute for a proper AGC connection within the metal junction box. Another common misconception is that you only need to ground the metal junction boxes if you are using non-metallic wiring. This is also not correct. The NEC requires that all metal enclosures, including metal junction boxes, be properly grounded, regardless of the type of wiring used. A third common misconception is that you can simply rely on the screws that hold the metal junction box to the wall or ceiling to provide grounding. This is not correct. These screws are not designed to provide a reliable grounding path, and they should not be used for this purpose. A fourth common misconception is that you only need to ground the metal junction boxes if they are located in a damp or wet location. This is also not correct. The NEC requires that all metal enclosures be properly grounded, regardless of their location. Finally, a fifth common misconception is that grounding is not important if you have ground fault circuit interrupter, GFCI, protection. While GFCI protection can help to prevent electrical shock, it is not a substitute for proper grounding. GFCI protection works by detecting imbalances in the current flowing through a circuit. If an imbalance is detected, the GFCI will trip, cutting off the power to the circuit. However, GFCI protection does not prevent fault currents from flowing through the grounding system. Therefore, it is still essential to properly ground all metal enclosures, even if you have GFCI protection. By understanding these common misconceptions, you can avoid making mistakes that could compromise the safety of your electrical system. Now, let's delve into the topic of bonding versus grounding, as these terms are often used interchangeably but have distinct meanings in the context of electrical systems. Grounding, as we've discussed, is the intentional connection of electrical systems and equipment to the earth. This connection provides a safe path for fault currents to flow, minimizing the risk of electrical shock and equipment damage. Grounding ensures that metallic enclosures, like metal junction boxes, are at the same electrical potential as the earth, preventing dangerous voltage differences. Bonding, on the other hand, is the process of connecting together all metal parts of an electrical system to create a common ground. This includes metal enclosures, metal raceways, and metal equipment. Bonding ensures that all metal parts are at the same electrical potential, preventing voltage differences that could cause electrical shock. In other words, grounding connects the electrical system to the earth, while bonding connects all the metal parts of the electrical system together. Both grounding and bonding are essential for electrical safety. Grounding provides a path for fault currents to flow to the earth, while bonding ensures that all metal parts are at the same electrical potential. Now, let's consider how grounding and bonding relate to metal junction boxes. As we've discussed, metal junction boxes must be properly grounded to ensure that they are at the same electrical potential as the earth. This is typically accomplished by connecting an equipment grounding conductor to the metal junction box using a grounding screw with pigtail. In addition to grounding, metal junction boxes must also be properly bonded to other metal parts of the electrical system. This is typically accomplished by connecting the metal junction box to the metal conduit or other metal raceway that is connected to it. The NEC provides specific requirements for bonding metal enclosures, including metal junction boxes. NEC Section 250.92 requires that metal enclosures containing service conductors be bonded to the grounding electrode conductor. It also requires that metal enclosures containing other than service conductors be bonded to the equipment grounding conductor. NEC Section 250.96 provides additional requirements for bonding metal enclosures. This section requires that metal enclosures be bonded to ensure electrical continuity and the capacity to conduct safely any fault current likely to be imposed. In summary, grounding and bonding are both essential for electrical safety. Grounding connects the electrical system to the earth, while bonding connects all the metal parts of the electrical system together. Metal junction boxes must be properly grounded and bonded to ensure that they are safe and compliant. Now, let's discuss some specific scenarios where grounding and bonding are particularly important. One scenario is when you are working with sensitive electronic equipment. Sensitive electronic equipment can be easily damaged by voltage surges or other electrical disturbances. Proper grounding and bonding can help to protect this equipment from damage. Another scenario is when you are working in a hazardous location. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dust. Proper grounding and bonding can help to prevent these hazards. A third scenario is when you are working in a healthcare facility. Healthcare facilities contain a variety of sensitive medical equipment that must be protected from electrical disturbances. Proper grounding and bonding can help to ensure the safety of patients and staff. Finally, let's consider the importance of regular inspection and maintenance of grounding and bonding systems. Grounding and bonding systems can degrade over time due to corrosion, loose connections, or other factors. Regular inspection and maintenance can help to identify and correct these problems before they lead to safety hazards. The NEC recommends that grounding and bonding systems be inspected at least annually. During the inspection, you should check for any signs of corrosion, loose connections, or other damage. You should also test the resistance of the grounding system to ensure that it is within acceptable limits. If you find any problems, you should correct them immediately. By following these recommendations, you can help to ensure that your grounding and bonding systems are safe and reliable.